Alright then, here's 7.3 part 2 where we're doing some more simplifying radicals. Again, radicals are just roots, so let's look at something like with cube roots. So with the cube root, again, same idea, we want to simplify that, pull out our perfect cubes, that's basically what it means. So we can take the cube root of each part, the 24, the x to the 5th, the y to the 9th, and the z 16th. Again, I think it's easier just to keep it one big radical, which would be like, okay, the beeper's on. Okay, so this time I'm looking for perfect cubes, with numbers in particular. So there aren't that many perfect cubes you really gotta know, but probably the most famous one is 8, and then the next one, that's 2 cubed, and then there's 3 cubed, 27. I'm looking at that, I go, I can see there's an 8 right in there. So it's going to be, whoopsie, 8 times 3. Excellent, so I'll be able to do the cube root of 8. And then we'll do the x's when we get to it. So again, I'm going to make it one big old cube root hat. And I'm going to pull out my perfect cubes. I'm going to pull the 8 out. He's going to become 2 on the outside. Cool. We can even put a light little line through him. So 3 stuck inside. X to the 5th, I'm going to do that thing again. I'm going to take the 5th, and let me do it over the side here. I'm going to go basically do 5, take the cube root of it to the 1/3 power, which comes 5/3. So that's equal to, and if you think of what 5/3 is, usually you don't like to do mixed numbers here, but that's 1 and 2/3. And so basically that means x to the 1st comes outside. I could put the 1 there if I wanted to, which I do. And then x to the 2/3 is left. So what does that mean? That means x squared to the 3rd root. 3rd root's taken care of over there. Had to tighten that up a little bit there. So we took care of the x. How about the y to the 9th? Let's see, y to the 9th. I'll go over this here just to show you what I'm doing, which is, get that out of there. Y to the, whoa, y to the 9th. To the 3rd power, which makes it not to the 9/3. Oh, and that comes straight out, y to the 3rd. So what does that mean? There's nothing, there's no any mixed number part to this. So what you got to do is just bring it on out. The 9/3 comes out because that's the cube root of 9 to y to the 9th. So you get y cubed here. Cool. So now, we've taken care of both this guy and this guy. Rewrote them as what they are. And then z to the 16th. What do you think about that? That comes out, again, it's z to the 16th to the 1/3 power, so it becomes 16/3, and you get z to the 5 1/3, which basically means z to the 5th comes outside, and then there's 1/3 left over, which stays inside, that's the cube root of z. And there you go. So we took care of each part. And there's your final answer. It's pretty, that's quite a mouthful, right? You don't really need the 1 there, too. I actually prefer not having the 1 there on the x. But there it is. That's simplified. Does that look better than the previous one? It's a matter of opinion. But you have pulled out all your perfect stuff as much as possible. So here's another example up here. And this also, we do this work our magic for these root stuff when it's fractional roots, things like this. So it's a radical over a radical, a fraction, but we know we've got the power to write it as one big radical. So again, we're going the other way. Instead of pulling stuff out, we're bringing stuff together all under 1. Now why that's helpful? Well, why is that helpful? Because if you broke down each one, if you broke down this one, and then seeing what you got, and then maybe then cancel out, reduce it that way, it's much easier to treat it as one big fraction oxal, and then cancel. Oh yeah, we can take out, this becomes 16, this, take away from this becomes x to the 4th, and this becomes y squared. So that's nice, that's a nice, which what you got is just the square root. This is all 1 on the bottom, so we don't have to mess with this. That's gone. So basically what you just have is, actually the fraction is gone. It's just all over 1. You have that. And we can do the square root of that nicely. What do you get? 4. 16 comes out. Ooh, and the x4th comes out. You're halving it this back to half root, square root. And then y. There she is. Okay, the one other problem I want to talk about is, let's talk square roots again. Let's do a square root of like something that is a big number. Let's say 162. Now, there is no exact, it's not a perfect square, but there are perfect squares in there. But say it's not that obvious what it is. One thing you can do is the old factor tree. Well, that's 2 times 81. Oh, and I know, but say you didn't realize 81 was a perfect square. You could just factor the heck out of this. Keep doing this. And then what you wind up getting, if you really look at it, it's 2 times 3 to the 4th. Because that's what we got here. And, you know, so if when in doubt, you can just factor the heck out of it, get it down to these prime factors, and then say, oh yeah, the 2's staying inside, but the 3 to the 4th here, this guy, he can come out. That's just take half of 3 to the 4th, which means, that means 3 squared on the outside, square root of 2. Which means you get 9 square root of 2 is your final answer. Cool. And, you know, that might have been easier if we hadn't kept factoring. If once you get that perfect square like we got here and say, oh, there's 81. I know 81. 81's our friend when it comes to square roots. It's perfect square. So then he can get the, come on out. So we want to take him, bring him on out. And how do you bring him outside? You got to take the square root of him. So you get 9 out here. So he is now gone. And then all that's left inside is the 2. Same answer. If I like working with I don't like doing the prime factors all the way. I like just finding those chunks of perfect square and then pulling it out, doing the trick. So, and if you went ahead with your calculator and looked at that, did 9 times the square root of 2, and then you also, with your calculator, did square root of 162, you'll see they're equivalent. Exactly they're exactly equal. Okay, so that's the end of 7.3. So on to 7.4. Why not?